Professor Banu Mohanty. He's Associate Chair at the Department of Physics and Astronomy, Michigan State University. He obtained his master's degree in physics in 1963 from the University of Allahabad and his PhD from the University of California, Riverside in 1968. He has served Michigan State University in various capacities for nearly 4 decades as assistant professor from 1970 to 76, associate professor from 1977 to 81, and professor from 82 onward. He has been a visiting professor at Bangalore, Mumbai, JNU, New Delhi, Madras, University of Antwerp in Belgium, and the Max Planck Institute in Stuttgart, Germany, and the Argonne National Laboratory in the US. He's a fellow of the American Physical Society. Please help me welcome Professor Mohanty.
Good morning. Theme of the conference, I thought I would talk a little bit about sort of energy and charge transfer in thermoelectric nanowires. And this is the work I have been involved. We have a project for the last several years trying to get the best thermoelectric materials for energy applications. And clearly the nanosystems are supposed to be playing an important role. And sort of a link is, if you think about nanoscience and technology, clearly the quantum computing has to come from that area. All the advancements of nanoscience has to be fully involved in the quantum computing, as you learn from all the talks. Even in the classical computing, as Professor Wolfgang Baur mentioned, as the system becomes smaller and smaller, the physics of nanoscience has to be incorporated in transports and dissipations and so on. But for my interest is, of course, energy and power transfer. And the reason is, of course, motivation for our program is that if you take a very quick look at the entire fossil fuel combustion through heat engines, you generate power at about 30 to 40% efficiency. The rest goes as very low-grade heat. And if you several estimates is 14 terawatts. The idea is to get part of that waste heat to thermoelectric. And the way we look at this thermoelectricity is basically a particle machine instead of this guy. And question is how we can make it extremely efficient and thereby get as much as possible. So that's the idea. And the outline of my talk is essentially nobody even 10 years ago, I did not know myself what thermoelectric was. So I'll just give you a one-page essential feature of what a thermoelectric is. And I'll talk about, since efficiency is the big game, what is the efficiency and what is needed to get a perfect machine, ideal machine. Of course, we cannot violate laws of thermodynamics. It has to be within the Carnot efficiency, since you are converting heat to some work. But even within that, how can I get perfect one? Then what can the nanostructures do, helping us to achieve that efficiency? And I'll just a couple of very interesting experiments recently carried out in several labs, and one in Caltech, one at Berkeley, and other one I don't remember, on molecules and nanowires to look at their response to heat, temperature gradient, and thermoelectric. And then I'll have some very quick summary and maybe what is going in the future. So essentially, we all know about standard Carnot engines. So you have a hot source and a cold source, and we want to transfer heat from this through a machine, a working gas, and we exchange heat here, then adiabatic compression, and then release it here. So, but it's all done in equilibrium. The system is always in thermal equilibrium. Of course, if you do perfect thermal equilibrium, it will take infinite time. So you do it a little bit faster. So in this process, of course, you dissipate energy. So you don't get the perfect efficiency. So the same idea is here. I have a hot source, cold source. I'll have particles, which I'll call electrons. And for the sake of convenience, we also talk about holes, as you will. and I exchange particles and holes from hot to cold end. And in that process, I carry energy, and hopefully, because they carry charge, I can use that charge transfer to generate a current or a voltage which can be used. So that's the idea of a thermoelectric machine. So a little bit of basic physics here. So I have, think of this little red element as a thermoelectric element, and I apply an electric field or a potential gradient, delta V, or a temperature gradient. Then I have an electrical current, which I call J, and a heat current I call Q. And so there is some exchange of currents back and forth. And the electrical current is, of course, a standard sigma E, electrical conductivity. But there is this, what is important for thermoelectricity is a cross-coupling, where in the presence of a temperature gradient, I'll have an electrical current. And that constant proportionality, for the sake of convenience, is written as sigma S. And S is called thermopower, or thermoelectric coefficient. And Q is the heat current. The same way there'll be a standard thermal conductivity, kappa. Also, there'll be, if you apply a field, there'll be some heat current due to cross-coupling. I'll be mostly interested in this. And the use is you can do this, either you have a temperature gradient which can pass a current. So that would be like a power generation. Or you can pass a current and use it to cool. So you can use the thermoelectric element as either a power generator or a refrigeration. In fact, some of the car cooling, the seats cooling is a bunch of thermoelectric elements. This object is going to play a very important role in all the physics and efficiency of the machines. And this is called ZT, and it's just the Z is a combination of several quantities. One is the electrical conductivity, and S is the thermopower, is square of that, and that plays an important role. And that's the operating temperature. If it's a hot and cold, T is roughly the average, and kappa is the thermal conductivity. So you can see, easily, if you can see just intuitively, if I have a very highly thermal conducting material, a temperature gradient, I'll sort of short circuit most of my energy source. I won't be able to produce enough power in the system. The problem is, of course, as you'll see, ZT is a dimensionless number, and the idea is to get the best ZT. So you will see all the papers, everywhere there'll be a plot of ZT and how they're doing it, how good one is doing. And that's a sort of a cartoon here is what you do. You take this is a thermoelectric element, you put a little burner, and you light. So it's converting heat to light. Okay, so let me give you some numbers because that's going to be very important. First thing is to what is the, if you go back and look at this one very quickly, what is called open circuit. If I don't have any current, J is equal to 0, so there's a relationship between the field and the temperature gradient. So delta T produces a field or a delta V. So if you go there, so essentially S is delta V over delta T, so basically volts per Kelvin. And typically, we talk about microvolts. It's not a big effect. If you can, of course, have volts per Kelvin, it would be great. But typically, it's microvolts per Kelvin. And it comes about from a fundamental unit. You can sort of think of EV as energy, KBT as energy. You use 25 millivolts, we know is 300 Kelvin. And from there, you can get KV over E is 25 millivolts over Kelvin, or if you divide by that, it's about 83. So this is a fundamental unit. And we measure the thermopower in units of that. Question is how large I can make it as a function of, is it 5 times or 1 time? So that's the number, or dimension and number. Typically, metals, which are very good conductors, which one would love to use them because ZT is proportional to the conductivity. I can make it very large. Unfortunately, due to a simple physics, they don't have large thermopower. That's the T83, but there is a Pauli suppression factor, KBT over EF. That gives you 1 microvolt, and is proportional to square of that is no good. So metals are not very good. And one way to think about it also which is where we think in physics that I have a metal, 0 temperature, I have basically no excitation, so nothing happens. So I heat it up, I excite some electrons from below the Fermi surface to above. I call them sort of electrons. Those which are below, I call them holes. They both have energy, they carry energy, but when they carry energy, but they have opposite charge effectively. So they cancel each other out, and that essentially gives to almost 0. So in many metals, if the number of electrons and the holes are identical, then you don't get any thermal power. So the game is to make them as disbalanced as possible. So therefore, metals are not good. So we have to find something else. It turns out narrow bandgap semiconductors are the best because they sort of optimize. If you have a wide bandgap semiconductor, conductivity is very less. And metals are bad. So somewhere in between are these narrow bandgap semiconductors. Typically, when I say narrow bandgap, it's about 0.2, 0.3 EV bandgap. And so they are the best thermoelectrics. And because they have about 200, you can even make it 500 sometimes. And this is a sort of a thing which we have to worry about if you are going to make a device out of this, because if it's a hot end, these are cold end. And if I have only, as I just mentioned, that electrons carry what we call N-type semiconductors. Electron have negative and holes have positive. And imagine yourself, here is a hot end. Electrons will come here, holes will come here. So now suppose I had only both electrons, then I'll have carry the current, but there's no way I can make a current flow. So in this process, if I have holes, electrons, maybe there's a little. So first the hot holes come in here, and the electrons come in there, but electron going there means the current is flowing here. So what is happening is in the end, when the electrons and holes flow, there is actually a current in this. So that's the geometry people use. They call it binary. So you have thousands of these doubles, PNs, 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 put them together, put a hot plate and a cold plate, then you have a thermoelectric machine. So that's how it is usually synthesized, made devices out of it. So there are many uses. As I also yesterday, we had a nice talk by Professor Rao. You could also use them. He doesn't use it, though. You can take these explosives, make a mini bomb, and blow it up. And so one end, you can heat it up and use the thermoelectrics current to detect how many active molecules you have. But he said he's not using thermoelectrics, he's using pyroelectrics. But I suspect thermoelectrics also would be equally good. I guess pyroelectrics are also responsible. When you heat it up, they produce, I think, what is the pyroelectric? Some electric field must be producing it. And we have been interested severally at low temperature thermoelectrics for some time. We have some, I'll show you in later a new system which was discovered at Michigan State at low temperature, one of the top, very good low temperature systems, but also last few years on power generation. That's where the main interest is now. In addition to, of course, thermoelectrics, there are many other similar physics machines, the thermionics, where you just excite electrons across a vacuum gap. There, the nice thing is that your gap, you can make it very, very low in thermal conductivity. So you can reduce that thermal. But they're not that popular now. I mean, people are working, but I don't know much about them. Of course, this is a famous case where I think Professor Patel's statement was that it's a perfect machine. I believe nature has made very little dissipation in the system, both photovoltaics and photosynthesis and electron transfers in redox systems. Okay, here is a little figure, and this is what I will discuss mostly. So I said you can use the thermoelectrics for either cooling. So there is efficiency in cooling called coefficient of performance. Let me not worry about that, although I have a figure for this. And in efficiency in power generation. So eta, you can see is proportional to this prefactor, which is just the Carnot efficiency, 1 minus TC over TH. So that's the best you can make, times a function. It looks complicated, but in that function appears this ZT. So if ZT, that dimensionless number, can be made very large, or say in theory, there's nothing which forbids to be infinite. So ZT is infinite, then you find you approach the Carnot efficiency. So bigger you make ZT, bigger efficient machines you have. So this is the same thing as plotted for refrigeration. Here is a GT being plotted, and here are the two temperature difference you have to maintain and cool. So this is a higher temperature, this is a low temperature, and you can see for a given GT, for delta T less, I have more efficient. And these horizontal lines are the standard refrigerants. I don't know much about R134A, but this simply says that if you want to cool across a 20 degree centigrade gradient, you can beat this system if you have GT of 3. So GT of 3 is sort of a holy grail now, and as I'll show you, there's some slow movement towards that number, but most of them are in this regime, so that's not competing. Okay, so let's do a little bit of what is a perfect machine? That's a very simple idea. I have eta is eta Carnot times this. So GT is infinite, as I said. If I make infinity, then this becomes 1. I get that. So what is the GT? GT, as I said, is a dimensionless number. Depends on all the electronic and lattice or phononic properties of the system. S square, sigma T, this, that. So you have some conductivity, some thermal power, some temperature. So only way I can make ZT an infinite if I have to make kappa lattice 0, kappa electric, because they're all positive quantities. They can't cancel, 0. So if phonon, which is the lattice thermal conductivity, the lattice carrying the heat from one end to the other end, if I can scatter them all, and it will be what is called perfect phonon glass. So a perfect phonon glass to make this guy 0, and to make K electronic 0, I'll have what I will call is ideal electron machine. So, so for the electronic physics, so I have kappa electron 0, I'll add ideal machine. So I'll talk. So if, say, I can turn off the lattice, switch off the lattice, they don't carry any heat. That dissipation path is gone. And then I make this charge and energy transport without dissipation by doing this. I have an infinite. So the question is, what is meaning? How do I do this? Or what are the ideas involved? Okay, so what is the reality? Of course, GT infinity is somewhere there, up on the universe, high up there. So for many, many years, GT was sort of hovering around about 1. And that's the reason why in 70s, say late 60s, 70s, all the excitement and research in thermoelectric died in USA and all over the world. Russians still continued producing lots of new materials, but somehow they thought GT never got beyond 1. But there are some theoretical ideas which were pushed in the middle 90s, and then which sort of got people excited to try new ideas, new things. And then this MBE growths came in. And so this is an MBE made sample of bismuth telluride and antimony telluride. We did some work on this. And they're quantum wells. They showed a pretty large, so suddenly there's a big jump. So there's something interesting was happening there. Then there was some, this is the one which I wanted to mention to you. I won't talk about it today also. This is bulk materials. So this is the one which was discovered in late 90s, I would say, in Michigan State, called bismuth bisium telluride. That's the sort of the best, was known the best low temperature bulk material. So this is a sort of a quantum dot system. So for bulk materials, still it is a good one. Then the lead telluride, lead selenide quantum dots gave a 2, which is pretty good number at room temperature. Then this was another interesting system which we were involved at Michigan State, which discovered last 4 years, I would say, at 1.8 at 800 Kelvin. It's promising materials, they're bulk materials, but it's very hard to work with this. But people like to have big chunk of thermoelectric materials to make generators, power supplies, and so on. I won't talk about it, but I'll just go to the extreme nano range and see what is the physics one can use to get this. So I want to reduce this that GT into two quantities: the thermal conductivity, which is the denominator, and the numerator is what is called power factor, S squared sigma. They can be connected, but people hope that they will control this one separately and that one. There is a point I forgot. Because they are semiconductors, the thermal conductivity of a semiconductor is dominated by lattice. If you think of a total thermal conductivity, you'll find about 80% is lattice through and 20% in this. Whereas in a metal, almost all through the electrons. So that also gives you a handle where you can manipulate that 80% that I said, this phonon glass idea, reduce that by a factor of 4, so that helps you. And then the electron part you can also tune in differently. So that is a good thing in a semiconductor. So anyway, nanosystems we don't have to talk about. We had a lot of lectures, this whole conference, and about 1 to 10 nanometer, about 10 to 100 angstrom length scale. And we know quantum confinement effects on electron becomes pronounced as you decrease the length scale. And so we should expect something interesting that is happening when I reduce to 10 to 20 angstroms. And we'll talk about quantum rods or wires today. Wells is what was proposed there. And also, as I also mentioned, that new materials are being discovered where you have bulk inside which nanoparticles are coming in or nanowires are forming, and they also can be controlled. If you can control them, their synthesis, then they are going to be very interesting, promising materials also. Okay, just to tell you a little bit about the temperature energy scale, this is what we learned in our basic quantum mechanics. First, you have a bulk material, assume a free electron moving in all 3 directions. Then in a quantum wire, I confine 2 directions. I just, for the sake of complete simplicity, I take A over A, and a length in this direction. So the transverse length where they're quantized is characterized with this energy scale. If I have a well, of course, only one direction is quantized, and this direction, 2 directions, they are, of course, free particles. So if you just take roughly an estimate of a nanometer length scale and a mass of electron, that's about 1,000 Kelvin. So at high temperature, we're operating 800 Kelvin. This is important to think about. Means if there are a couple of channels along the transverse direction, I have to worry about both of them. So that's sort of an energy scale. And so why does it affect the transport? Because one of the important quantities which sort of controls the transport, and in fact, many physical properties of electron systems is this density of states. How many energy levels accessible to the electron in a given energy range ED. So this is the standard parabolic, poorly drawn 3-dimensional. Then you go to 2-dimensional, you make some kinks, some structures in this, and 1D you make that. So you can see here is a very interesting, simple, suppose my Fermi energy was somewhere here, the density of states is almost flat. So when I excite electrons thermally, I create holes and electrons. Because this is so flat, I'll have roughly the same number of electrons and holes. So that's the reason why a metal in 3D is not very good. On the other hand, imagine in this system, if I put in here the Fermi energy, because there's an enormous difference in the density of states above and below, I will have different number of electrons and holes. So that's essentially really the physics, which tells you why going from here to here, I'll have some changes in the property. And that led to a very simple calculation, which actually was the initiator of a lot of funding in this area, was a calculation by a student of Millie Dresselhaus, who is sort of now a big shot. I mean, she is sort of involved in all thermoelectric research now in USA. So what she found in a very simple calculation, that if you go from a bulk to a 2D to a 1D material, and you reduce this length, confinement length, then you can get an enormous increase in this GT. So from 1 to, if you think, is this. So that sort of get people excited, and now that the fabrications of quantum dots and quantum wares are being made, they started attempting to test this idea. So it turns out this is very naive theorist calculation. Many things are sort of put under the rug, but certainly the idea is that if you publish a paper like this, it was published in '96, I believe, and you are also well known, you might excite other people to work and also funding to come. So there are many, in fact, part of our reason we got funding was trying to understand this stuff. And as I said, this thermopower is proportional to the derivative of the density of states near the Fermi energy. If it's flat, it's 0. If it's a sharp singularity or some structure, then I can get Lars. Okay? So I will tell you a couple of experiments. So what is the attempt to do this? And I will tell you a beautiful experiment done in molecules, just a simple molecule. Of course, eventually the idea will be to put all these molecules on a surface and use them as your thermoelectric machines. And then I'll talk about 2 experiments on nanowires and some theoretical ideas or calculations here. Okay, here is a nice work which was done, published in Science by Reddy. It's a big group. And what they did was to take a substrate of gold, which they could then make it hot or cold temperature. And then in between, there's a tip, STM tip, coming from the top, and then trapped a molecule. And these molecules, they could control essentially benzene rings 2, 1, 2, 3. As you do that, of course, we know the electronic, there has to be an electronic path in which they are trying to monitor, because the electrons from one metal to other metal has to go through that, and depending on that, where that electron level is, either it can go like an electron, or it can go like a hole, and you can really measure that. And that's sort of a beautiful experiment, and, and you can change this. So what they did is first, they, without any temperature gradient, and brought it in and measured the current voltage, made sure there was some link. Then once they had the link, they stopped there, then they heated this sample, and then they measured. So here is some experiment where they measured the voltage, no molecules, this is the sort of a bar, and then in the presence of molecule, they did it. And then, of course, what they're doing is they're pulling it, and as the distance increases, of course, eventually it snaps, and you get the voltage gone. Here, this is gone here. So then they looked at this, whatever the voltage at different temperatures. As you can see, that different temperature gradient is increasing. So this is 30 degrees, this is 10, 0, 10. So there is something thermoelectric is happening, because I'm changing the temperature gradient across this, I'm increasing that. So that was sort of their clue that they're measuring sort of thermoelectric response, not of that molecule really, it's of that system, because they all form a combined group. And of course, these are one molecule experiments, so they had to do millions or thousands. These are statistics. As you can see, the delta T changing, this whole thing moves. And they also measured the voltage as a function of temperature. From there, they could figure out this thermopower. It's not big. It's not big. It's only about 10 microvolts. But who knows? Maybe I can put a beautiful array of these molecules nicely ordered, which is possible by self-assembly. I can get a much bigger response out of it. But something interesting happens from this measurement. It's not, of course, practical applications, but you can use it as a spectroscopy using thermopower. Idea is the following, and this was a simple theoretical calculation. You take 2 metals, put in a molecule, some state here, then you can compute the sort of a transmission coefficient, standard quantum mechanics, and as you change the Fermi energy of the metal vis-a-vis these are the HOMO of the molecule. This is HOMO means highest occupied molecular orbitals. LUMO means lowest unoccupied molecular orbitals. These are the 2 levels. As you tune, as the Fermi energy hits this, there is a sort of a resonance transfer. Now you can use that and compute the thermopower, pretty straightforward. Essentially, once you have a temperature gradient, there's a formula. You can calculate thermopower as a function of the chemical potential, and you plot it. what you find is, interestingly, that now you know your measurement, you put it in, so you can locate where the HOMO or LUMO is vis-a-vis the metal fundamental energy. So it's a nice experiment which tells us how I can use this nano thermoelectricity for doing spectroscopic measurements of molecule levels. May not be the most efficient, but that's a... Okay, so what is happening in the... these are real attempt to make systems which are going to be useful in the future. These are also, we learned a little bit about this system called anodic alumina. So you take aluminum oxide by some means, which I don't know. They make these beautiful holes, goes right through that, pretty uniform in size. And then once you do that, then you fill up those holes with thermoelectric materials. The point is these are, of course, 70 nanometers to bigger than that. They're not very nano, 70 to 100. There are other issues here. Then when you try to put metals in, there is no guarantee. It has to go on this end and that end. So sometimes it doesn't have contacts. So there's some ideas where you fluctuate the voltage, come back and forth and fill it up. But these were earlier attempts, 2003. So you can see it's about 6 years back, 5 years back or 6 years back. And this is, in fact, nothing much happened. So people lost some hope in this thermal power through nanowires. There's other problems also. In 1D, as we know, there's a lot of scattering, electron-electron interaction effects. So they're not very popular. Until last 2 years, some extremely interesting experiments came. So I think there's a lot of new revival of it. So these are, of course, beautiful samples made by the Caltech group of Heath. And this paper came out. So these are silicon. Silicon is, the whole idea is to make silicon because we have a lot of silicon as our part of computing world. Silicon dioxide, silicon is cheap. So they wanted to make silicon nanowires. And this green stuff, which you can't see, I guess, from the back, are a bunch of parallel nanowires, which they developed the technique to make. And all, of course, this is the machinery of measurement. You can see world is quite hard. So whether it's the efficient way of using energy, we don't know, because the amount of money and energy you spend to build this is perhaps much, much larger than that power output. But what you found was a very interesting result. And there, when you made this nanowires of silicon, bulk silicon's thermal conductivity is over 150 watts per minute. Then what you find here, here I'm plotting bulk by nanowire is dramatic, about factors of 100, 200, things like that. So translated to a simple language, when I make nanowires, the phonon, the heat conductivity reduces dramatically by 2 orders of magnitude. And that's, I think, is a big gain in this whole field. If you can reduce that phonon conductivity by a factor of 100, of course, this is too big. So therefore, bulk silicon is not good. This GT is 0.01. But by reducing this by 150 by a factor of 100, you have a tremendous increase possibility. So that's point number one. The point number two is also, which is unique and which I don't think, I don't understand very well, neither the people, need some theory to be done carefully. They have some ideas that if you think about bulk systems, this is the thermal power, S square of that. There's enormous enhancement. There's some sort of resonant effect near the 200 temperature range. That's, again, part of the nanowire system. That what is here, there's the electron thermal power, but electrons interact with the phonons also. There's something called phonon drag. And so there is sort of because of the nanowire, the phonon scattering is changed. So this leads to this effect. That's what they guess. I have not thought through it much, but if this experiment is right, you can see there is an enormous enhancement in the S itself. So you have reduced the thermal conductivity by a factor of 100. You have increased S by this, so you can see that you have really made a big gain. In fact, what you find is this GT is what I want, is you can see here 200 from almost 0.1, maybe less than that, to 1. So this is making a big excitement because silicon getting GT1 is, I think, is going to be very useful for this area. If there's only one experiment, you always doubt. You never believe an experimentalist unless somebody's done independently. Of course, you never believe a theorist anyway. So, but this was the other experiment which was done. I'll just, see here is, unlike the Caltech group, where they grew beautiful nanowires, very well-characterized surfaces, these people had two experiments where very well-characterized, nice nanowire surface. This is silicon nanowires. And here there's another one which was rough. At certain lengths, there's some modulations, rough interface or surface, and these are these nanowires. One thing they found, which was common with both, the other experiment, there was again a dramatic reduction in the thermal conductivity as you went from 115 nanometers diameter nanowire to 50. And several concentrations were used, and so these experiments need to be, again, carefully analyzed, but the net effect is a reduction in the thermal conductivity by a large amount. And what they do now compare with what is called, this is the amorphous silicon, they're coming pretty close. Now you can see here that, again, I want to mention what is the status here. This is an important, so if, on this side, we are plotting, this curve is the thermal conductivity, bulk to nanowire. So that means you are reducing, again, we're talking about 10 to the 4, 10 to the 3, 10 to the 2, 100 orders of magnitude reduction. But unfortunately, electronic conductivities are not good, as we expect. Bulk silicon is a beautiful has long mean-free path and good transport. And so what happens here, this S squared, the numerator here is reduced by a factor of 10. So you gain through this, you lose through that, so the net upshot is about 0.5. So again, you have gone from 0.1, 0.01, 0.05 range to a fat 0.5. So this is very helpful, and so now people are trying to use the same technique, although silicon was good, but to start with, silicon was not a very good thermoelectric as a bulk. So why not take a very good one, like bismuth telluride or something else, and make nanowires? Whether it's possible or not, we don't know, but that's the plan for the future. So what about theory? Where is the theoretical idea? So I said, we are looking for a perfect machine. So where is that perfect machine? So where does theory stand? One thing we have to know as a theorist is we're talking about nanowires, we're talking about room temperatures, and the question is the transport. If, to do theory, I must understand whether transport is quantum transport or ballistic transport or diffusive, where the electron moves, scatters with phonons, there's a mean-free path, and then the nanowires diameters are large compared to mean-free path are small, so I have to worry about those. So one calculation which was done nicely recently is taking some actual calculation, good calculations, taking some sort of a channels, transistors. If you think about silicon channels, oxide barriers, and if you just naively think about two extreme limits, if there's a ballistic movement of electrons going through these channels, then you have this quantum conductance, or inverse is resistance, 2e square over h, then the number of channels the electron is going. So that essentially tells us the ballistic limit. Then on the other hand, if you have a diffusive, the electron goes, scatters around, there is a mean-free path, then we all know from our transport theory, resistance is proportional to L. So what the people did was a good calculation using Green's function techniques, where you then put these layers and they did reasonably well some electron phonon, electron impurity scattering. Then you compute this resistance versus this. They're only in a very small, 1 nanometer to 1.5 nanometer is what there is anyway. So if your channels are 2, 3 nanometers, and maybe, of course, this way is very long, so it's not necessarily, most likely for practical use, we are not in the so-called ballistic regime, but rather in the diffusive regime. So we have to do diffusive calculations. And one way to do them, these calculations, which we do, is, sorry, I'm using this one. Using, this is the only slide, I won't go through the equations. I'll just tell you, so this is what we do. That's as a theorist, we do have to do equations, calculations, computers. As Professor Wolfgang Bauer said, we do use heavy computations. So, but this is all is needed in a calculation. So you have to, these are all Fermi functions, conductivity, thermal power, thermal conductivity. This is a point I'm going to bring back in a minute. And everything depends on this factor, which called sigma E, transport function, which depends on the electronic band structure. This depends on the band structure. This depends on the scattering. So the standard thing is, in fact, I'll show you one result we do, that we take full ab initio band structure calculations for these materials and compute this very carefully. And this one, we don't have much of a handle. We are still struggling to understand this tau of E. And then we put it in and then do calculations and see how they are. OK, here is something I wanted to mention, because I'll come back to this. This is the same old equation I wrote down in the beginning. And this is an important thing which is missed by many people. This didn't matter for metals, but it's becoming very important for this thermoelectrics. If you look at current, it's this. And this is a heat current. Now imagine I have a constant current, because most of the measurements are done at constant current. Let's say constant current, but J is equal to 0. Then given a temperature gradient, I have a field generated internally in the system. Now I go back and put that field in this heat equation. Then what I get is an effective conductivity, which is the constant current conductivity, thermal carried by the electrons, compared to the constant field. So this is what we experimentally measure. This is normally we use theoretical calculations. But however, there is an important result here that these two, this has to be positive by definition. They are response functions. This is positive. And so question is how best this can come. Because experimentally this is what is used, and I told you to get a perfect thermoelectric, I must make this 0, which means these two guys perfectly cancel. So what is the physics such that these two guys will perfectly cancel? So my electronic thermal conductivity at constant current is 0. I get the best electronic thermoelectric. So that's the idea. So this is a calculation which it was done in a nanoware, for silicon nanoware. As a theorist, you can see theorists are much more optimistic. So you can change the concentrations, you can change they change the size. And we are now limited, unless we get next generation computers, to treat about 300 particles ab initio calculations. But we need about 1,000 particles, which is sort of a next game. We can't handle them. But what we find that depending on the thermal conductivity of the lattice, you can get GTs of. But I believe there are other issues. These numbers are too high from theory, but we'll see how these numbers come down to relate to experiment. One thing you should know that these are sort of much narrower nanowares. It is, I forget, there was some size here. It's 1.1 nanometers. But the actual experiments are, here is 3, and there's 1.1. Because I can't do big nanowares that well. OK. So now I have 2 slides to tell you where are we going. What is still a perfect thermoelectric? These are all 4, 5. I need infinite. So here is an idea which was proposed. And this is where the theorist's idea of making that nano. Now imagine, and this is perhaps what nature has done. If I know my, I think you referred to all this entropies. This is von Neumann entropy, which we use in our entropy of electron moving in it's an electron in a solid. And Fermi-Dirac distribution function is this. And you can see that this is related to entropy. If I just change the entropy by adding a particle, essentially this E minus mu over TR. So the idea is that if I take the electron hopping from site to site as it carries charge and energy, if I can guarantee that this guy, E minus mu r over TR, is constant. I have a temperature gradient, high temperature, low temperature, temperature gradient here. And typically, I have an energy level of the electron. Now, if I can tune my chemical potential by applying some fields, and so that I keep this as a constant, then I have essentially, I add a particle at a site, but I don't change the entropy. So it's an adiabatic transport. So and as we know from our physics, adiabatic transport is no dissipation. So that was their idea, that if I can make a thermoelectric where this is the energy level in which the electron is moving, which is, of course, a single energy. An electron doesn't move in single energy. A single energy, but I tune as it goes from hot end to the cold end. I connect it to something, and I change the chemical potential. Then I'll get a perfect machine, adiabatic. Therefore, there'll be no loss in the electronic system. So I should get, if there is no phonons in the system, infinity. A beautiful idea. In fact, they got some funding to try this. Has not been successful. But I want to link that idea to what we calculate. And this is what I told you last 2 slides back. The electronic thermal conductivity as a function of J has 2 pieces. What you find that if you do this idea of change the chemical potential and with the temperature, demanding this to be a constant, this is what the calculation is, then you find that GT at here is, as you tune the energy levels, you find both. One thing you find that the thermal electrical conductivity goes to 0, which means this, this guy exactly cancels that, and you get enormous this. So this is an idea which maybe 20 years from now might be feasible. I had a slightly different idea that don't change the chemical potential, which is again connecting, but maybe allow for different energy levels, the hot and cold end, but that would be, of course, again, one shot. You change the energy levels so that E minus mu is a constant. So you synthesize charge. Maybe nature has done that, makes various molecules as sites where the electron goes here, 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 optimally, so that that factor remains constant. There's no entropy involved, change. So, but this is an idea which is still, I like it, and I think this Linke is working on it. I talked with him once in a while. Humphrey, who is a graduate student, proposed this. She has moved on, working on quantum transport, but let us see. Okay, so that is the end of my talk. 2 concepts, what I think I would like you to take out from this lecture is the concept of a phonon glass, which is becoming better and better with these nanoparticles with surface roughness. Then adiabatic charge transport, which is a good idea, but still not possible. Nanowires are pretty close to the phonon glass. You can reduce even below the amorphous silicon limit, but electron transport a long way to go. Experiments are done at 1.3. Maybe we need them. The theorists are working in this. Experimentalists are 10 range. And we need better transport calculations, particularly the understanding of the relaxation time and sort of the coherent interplay of the phonons in these nanoparticles and systems and electrons, electron structures of that. And thank you.
Okay, thank you, Professor Mohanty. There's time for some questions.
The electric conductivity is not affected.
Electrical conductivity is not affected.
Doesn't go down to?
It doesn't matter. Well, let's see. If electrical conductivity, if I can, in the ideal situation, phonons are very gone, let us say. Electrical conductivity can be less, but if I make the denominator 0.
Exactly 0, you're
exactly
saying.
Exactly 0. So I have to go, that approach that 0 faster than the electrical conductivity.
Yeah. Because now if also the numerator goes to 0 in the same way, then...
But let me just, this calculation is not necessarily, yeah, they didn't, you are right. They should have a calculation of conductivity, which I think they have, I forgot. It does go down.
So there was that expression where I think that's what he was referring to, where the denominator was becoming 0. So ZT was actually getting to be infinity. Is that really possible? I mean, has this been experimentally realized?
No, experimentally not realized. Experimentally, what is realized, I think, in fact, See, in a problem, in experiment, unfortunately, when you measure the, let's say GT, is S square you can measure, sigma you measure, T you measure, then here is kappa, right? Unfortunately, thermoconductivity doesn't care whether you're getting to electrons and so on, you measure the total, okay? So once you measure the total, so you don't, it's a phonon, it's a lattice, plus this one, that k electron minus S square sigma T. I measure both, so I don't know how to do it from experimentally. But one way to do that is inject some theory, or do the following, which people do, which is not quite right. They simply use some old rules called Wiedemann-Franz, which breaks down really dramatically in this limit. When this exactly cancels, all these metal theories are wrong. So what one could do is to estimate this theoretically, estimate this theoretically, and see how they are. That's what we have been approaching. And what we find even in this lead telluride, we haven't done it in this, because I didn't do calculations in nanoware. I can go back and check it. But in lead telluride, we could get this to be a 50% reduction. But you know that 50% is easy. But next 50% is 10 times harder, and the next one is 100 times harder, sort of.